It's so good to be here and see all of you, lots of familiar faces, some new faces. I'm really excited to be here talking about OpenSearch with you guys and with the community. As Lisa mentioned, I'm going to talk about OpenSearch since we joined the Linux Foundation. But really, I'm here to talk about community-led innovation. And I'll be joined by some members on the stage from NVIDIA and SAP who really exemplify the spirit of innovation and collaboration. A year ago this month, OpenSearch transitioned to be a project of the Linux Foundation. At the time, we launched the OpenSearch Software Foundation as a nonprofit organization under the Linux Foundation to support the OpenSearch project with marketing and building awareness. This brought vendor-neutral, community-driven governance to the open source project. And I hope you all join us tonight to the reception to help celebrate this anniversary. When we joined the Linux Foundation, there was really three key goals that drove this transition. One, open governance, to invite and encourage more organizations to participate and to lead OpenSearch forward. Open collaboration, to make it easy to advance how we all work together to grow OpenSearch. And really with both of these things, we were highly confident we'd be able to continue to accelerate innovation in OpenSearch by having more people work together more openly to be able to more quickly develop this product into the future. And I'm pleased to report in the first year we've made great strides on all of these objectives. When we talk about open governance, what we mean is community-driven, community-led, and independent. And the OpenSearch Technical Steering Committee is like a really good example of this. This is a group of 15 technical leaders across 10 organizations who are chartered to lead the technical direction of the project, and they're already playing a vital role in steering the product forward. Selected last September, membership of the TSC is designed to recognize technical leadership and is based off of merit. They are elected from the maintainers of the project. They don't need to be a member of the Software Foundation or provide any funding to be an active leader in driving the technical direction of the project. The OpenSearch Software Foundation is governed by a governing board. This board is drawn from the 16 organizations who contribute financially to support the project so that we can drive more awareness of the project and host events like this so that we can all be here today to work together. I am honored as a member of the board to work with other members from AWS, Aaron, DataStax, and SAP to help oversee the work of the foundation. And then when you talk about open collaboration, since we moved into the Linux Foundation, we've taken concrete steps like picking up the whole GitHub and moving it into the Linux Foundation, moving all of our build and infra into the Linux Foundation. And the results have been fabulous in the first year. We've already received over 8,800 contributions to the project from over 3,300 different contributors across 400 organizations. And we've moved from number 70 to inside the top 20 amongst Linux Foundation projects based off of active contributions. So these are all really good signs that the work this community is doing is thriving and that we're really taking this project forward. So I couldn't be more pleased on that front. And every contribution is important. Every contributor who's adding to the project is helping make this project better. But one thing that really does stick out to me is that we've seen some of the biggest names in the industry begin contributing to OpenSearch. And not little contributions. These are like big contributions that take sustained engineering effort in order to achieve. This to me is a really good sign that lots of companies are beginning to bet on OpenSearch as a core technology that they're building solutions on top of. And these are just a few examples in the project features from organizations, but we've also seen really valuable contributions from including engineers at Apple who recently enhanced core search functionality. In fact, I'm excited to announce that the core repo recently elected a new maintainer from Apple's engineering team. And the ultimate goal of this collaboration is to drive innovation, to build better, faster, and I'm looking forward to hearing from two of these in just a few minutes on their work on OpenSearch. So I also want to take a moment to highlight performance, because to me this really exemplifies us investing in committing for the long-term health of the project. No data engine ever went sideways by being faster or cheaper, so these things are always good. And to the left is better, and down is better, and the scale, in order to fit it on one slide, we actually had to use a log 10 logarithmic scale. So this actually represents a 10x improvement in performance during the 2.0 line to the 3.0 launch across the 5 key measures that we were measuring in our benchmarks. So this is huge, and it's just the beginning. So truly, in May, we launched OpenSearch 3.0, which was a giant leap forward for OpenSearch, not only in performance, but a dramatic advancement in capabilities to address the needs of today and tomorrow's observability, search, and AI applications. This included, beyond performance, we transformed how data management and transport works, a lot of enhancements to the vector engine, and new capabilities across search, observability, and security. We also, since we release every 8 weeks, we've had 2 subsequent releases, 3.1 and 3.2, both of which continue to add more and more capability to the OpenSearch. The latest unlocks so many of these capabilities, including vector search. We've added memory optimizations, new algorithms, and can now support up to trillion scale operations. We added native agentic AI support through MCP, or Model Context Protocol, the GPU acceleration for vector index builds, which we'll actually hear more about in just a minute. We added agentic search, which enables natural language workflows and agentic memory so that you can carry context through AI interactions. And expanded our piped processing language, this is the language we use in a lot of observability and security cases, by underpinning it with Apache Calcite, which now allows us to do much more complex analytical queries through simple PPL functions to just add a lot more analytical power to OpenSearch. And if any of you have worked on the build and test and release process for OpenSearch, I'm sure you're probably very excited about the last one, which is Oscar, which is a new AI-powered release bot designed to automate the release process, which for a project the size of OpenSearch can be pretty complex. So I'm really excited about that one as well. Probably not as much as the people who have to spend a lot less time doing releases. So these improvements demonstrate our commitment to OpenSearch, to the community, and has made innovation and performance at scale. And if I'm speaking about innovation and performance at scale, what company comes to mind immediately is NVIDIA. Their continuous innovation has helped developers around the world achieve the unprecedented. It's my pleasure to introduce Corey Nolet, who's here to talk about NVIDIA's groundbreaking work in vector search. Please join me in welcoming Corey.
Thank you, Carl. So I am here today to talk about, as Carl mentioned, accelerated vector search, its use in vector databases, and I'm going to go over our new library for vector search, accelerated vector search on the GPU called cuVS. My name is Corey Nolet. You'll notice I qualify my name with my middle initial. So a couple years ago, funny story, my colleagues reached out to me and congratulating me for a paper that I had published apparently on single-cell genomics, and I found out that there is actually another Corey Nolet. Oddly, he also attended my father's alma mater in Massachusetts, UMass. So I qualify my name now. He's oddly also a software engineer and has published research in genomics, which I also have as well. So it's very, very weird. So I'm a principal architect at NVIDIA. That's another way of saying I get to work with massively talented individuals day to day, solving really challenging problems that are relevant to today, looking forward to tomorrow, which is also another way of saying I lead engineering for a few different libraries at NVIDIA, specifically for vector search, which comes out of classical machine learning and data mining primitives. I'm sure most of you by now have heard the term vector search, at least know something about vector search. I'm not going to spend a whole lot of time giving a background, but just a real brief introduction, right? I take multimedia, I create vectors out of it. Back with classical machine learning, we used to do that manually. Now we do that automatically with embeddings, deep learning models that can encode the information in vector form. And if I want to look up similar multimedia, similar videos, similar audio, similar items inside of an image, I would encode that into a vector, and then I would look for similar vectors, right? I can perform what we call a semantic search. And so several algorithms exist to be able to perform vector search. One of the most naive and simple algorithms is brute force, right? Exhaustive search. Put a bunch of vectors in a list, right? And when I have a query vector and I want to find similar neighbors to that, I exhaustively go through each list. I can't sort, right? This isn't like traditional database indexes, the structured indexes, keyword search indexes, where I can leverage sorting in order to, reduce my space here, right? I end up having to calculate the exhaustive distances between all of the vectors. It doesn't scale, right? It is actually more efficient than you would think, both on CPU and on the GPU at small scale. It can be more efficient than using approximate nearest neighbors techniques, which is what we tend to use at scale. These approximate nearest neighbors algorithms are machine learning algorithms, right? They approximate the result. They come with trade-offs. I can trade off basically the quality of the approximation for the speed of the search. Two common categories of these algorithms are tree-based and graph-based. Another name for tree-based, you'll hear IVF, inverted file index, as it relates to vector search, and global index, for instance. And graph-based is pretty much the state of the art today. That's what many folks are using. These two are not mutually exclusive. People use them together. HNSW, popular graph-based algorithm. You may have heard it if you have used the vector search capabilities in Lucene today. But we know that unstructured data is growing at an alarming rate, right? For the past 7 years, since 2018, it's been growing literally exponentially. It accounts for most new data that's being used today. Organizations aren't even able to use the sheer volume of data that they have available. It takes a while to embed. It takes a while to index, right? They're not even able to answer their problems yet because they're still dealing with the AI problems inherent in today's generative AI solutions. Indexing is also very time-consuming. Last year at this time, trillion scale was brought up by two hyperscalers. That was Microsoft and Google. We're hearing that weekly now. We're sitting in meetings with different partners, customers, users. Trillion scale is being brought up more and more. It's very obvious we need a solution at trillion scale. So now I'll do a little shameless plug for NVIDIA cuVS. This is our open source library for vector search, for accelerated vector search on the GPU. cuVS is not a database. It is a vector search library. So it is essentially a machine learning library that is capable of building vector search indexes. It's fully open source. It's Apache 2.0 licensed. We build it on top of a base set of primitives, so it's got CUDA underneath. It uses a lot of our really low-level libraries. We have a library called Raft, which is a library of machine learning primitives that's shared across several of our other libraries. It exposes several different languages to make integration easier. And contrary to popular belief, you don't necessarily need to fit your entire data set on the GPU to train a vector search index on the GPU. So we have out-of-core capability inside of cuVS as well. Typical pipeline for vector search would look like this, right? We've covered the vectorization, whether they're manually engineered features like a row in a database, and I'm coming up with categories and different summary statistics, have a domain expert kind of figuring out which ones make sense for search, or I'm using a deep learning model for doing the vectorization. Oftentimes, I will build an index. I'll have that as a separate step. And then I'll put that index into an inference, into production. For most production workflows, you're going to have some interaction with storage, right? For durability, you're going to want to store your vectors down on disk, and then you'll probably load them up, build your vector index, and then serialize that back to disk. And we tend to find two different major categories of use cases, right? One I've kind of mentioned, semantic search, right? I have semantic information encoded in this vector, and it's got some geometry with respect to the other vectors, and I want to look up that vector, which will show me similar things. But a more subtle use case that I think a lot of folks are starting to realize. Now, we've been doing these machine learning things for a while, these data mining algorithms for a while. Vector search also comprises the bottleneck in most of these data mining algorithms, right? I call them neighborhood methods. This is one of the topics of my PhD. But imagine these visualization algorithms, right? They're very relevant to deep learning. They're very relevant to generative AI, where I want to be able to visualize these points maybe in 2 or 3 dimensions, right? If I'm doing single-cell genomics, I want to visualize my cancer points and my non-cancer points, and I want to visualize and see and reason about how those things differ. These are almost never a one and done. They're usually a batch operation. These days, GPUs are making them interactive, which is pretty amazing. This is a whole other side of vector search that I think a lot of the people that are more interested in RAG and generative AI aren't even aware of. We're seeing these two communities finally come together. It's wonderful. But data mining is more focused on offline, throughput-intensive problems, right? Where I'm trying to squeeze as much data through the GPU as I possibly can. Semantic search is usually about, okay, I have a user, clicked on an item on a website, right? That item, a vector, gets sent to a back end on a server somewhere, right? That server has to be able to produce the closest items with very low latency, very fast, nearly immediately, right? A few milliseconds before that user starts clicking in other areas of the website, right? So it's a latency-sensitive problem. And multiple users are going to be sending these to the back end, right? And it has to be able to process them individually. I care about the time that it takes to get that result. Data mining problems tend to care about the throughput, right? I've got 1 billion vectors that I need to visualize. How fast can I crunch them through the GPU? On the CPU today, it takes days, right? We're making problems literally tractable that we couldn't do before. Clustering algorithms, manifold learning algorithms, dimensionality reduction algorithms, all of these data analysis algorithms that a typical data scientist uses. And so putting this into perspective, we have batch parallel processing, which is the throughput-intensive problems, and then we have online streaming, which is more the latency-sensitive problems. These batch parallel processes also include the index building, right? If we did our job right, then we should be able to have a throughput-intensive problem in the index build itself so that we can use the GPUs to crunch through that. Pre-processing, quantization techniques for being able to shrink the footprint of the vectors, clustering, these are all throughput-intensive problems. And that's not to say that the online streaming processes, those are extremely useful on GPU as well, right? Search specifically, being able to add vectors to an existing index as well. If we do our job right, we should be able to lower costs in some way. It's not always possible, right? But if you can repurpose a GPU after using it for something different, like actually doing your embedding or doing your LLM, you can have a cost saving there. High performance tends to generally relate to lower costs. So HNSW is a graph-based algorithm. It is an algorithm that on the CPU is built one vector at a time, right? I can do it in parallel, generally requires that I have to lock or somehow have to be able to mutate a shared state. I can do that without locks, right? We know that, but we're limited in the amount of parallelism that we can actually expose, right? At some point, I've got to bring things together. Instead of trying to mimic this algorithm directly on the GPU, we kind of took a step back and said, how can we reframe this problem and create an algorithm that could be a throughput-intensive problem so that we can take advantage of all of the cores on the GPU and we can build a graph that really fast on the GPU. And so that's where this algorithm CAGRA came from. We have a lot of different algorithms in cuVS. CAGRA is the one algorithm that is completely novel. We built it from the ground up specifically with GPU in mind for both build and for search, right? So when I have 10,000 vectors that I need to search really fast in parallel, I can take extreme advantage of the parallelism of the GPU there. When I have one vector, I can still take extreme advantage. I can be searching in parallel through that graph. But I can also build an index really fast as well. And so this isn't just for CAGRA, this is with most of the index algorithms. We tend to notice that the build time increases as the quality of the index increases. The quality here being measured in recall. That's if I did a brute force on this data, and I did my approximate algorithm on this data, how many of those brute force, those exact results would I get back when I do a query, right? And I take basically the set intersection of that, and that becomes recall. So the quality increases. As the quality increases, my build time, because my model gets more complex, right, my build time increases. As dimensionality, as the more information that I encode in my vector increases, build time also increases. And as the number of embeddings, the scale increases, then build time increases. But being able to build and search on the GPU, that's a great feature, right? The unfortunate thing being that when you search on the GPU, you do now have to have memory resident in the GPU. You have to allocate the GPU. If you don't necessarily have a high volume search, right, most of today's generative AI workloads like RAG don't necessarily have a high volume search yet, right? We're not generating the queries yet at high volume. We tend to find that the latencies are fairly high end to end, not just for the vector search, mostly for the LLM. The LLM is on the order of seconds. I really don't care if my vector search takes 2 milliseconds, right? So why even bother having the GPU in the mix for that, right? So this kind of brought us to this idea that why didn't I set, and you'll see later, this isn't necessarily a novel idea, so I'm going to give credit where credit is due, but this notion that I can build my index on the GPU, right? And then after I'm done building my indexes, working off my queue, I might be able to repurpose that GPU for other things. But then I can convert it to the CPU for search. cuVS is not a CPU library. We're not building a graph-based algorithm on the CPU for search, especially not when everybody's using HNSW. So what we can do, we found out, HNSW is hierarchical. HNSW has a small world degree distribution. Each of the nodes, it's small world, right? You have your Taylor Swift nodes. Very few of the nodes are going to be connected to most of the other nodes. And then you got most of the nodes aren't really that connected, right? CAGRA is what we call a flat graph, right? There's no hierarchy, and it's a fixed degree. It's usually a fairly small degree, but it's fixed degree. That's what allows us to extract all that parallelism from the GPU. But it turns out that we can convert a CAGRA graph really easily to an HNSW graph and preserve the quality and preserve the performance. And so vector search, right? We're making great progress there. We have great algorithms. Now we want to try this out in vector databases, right? Usually we'll take a vector search library and then we'll plop that into a vector database, right? I'm going to choose to allow this database to remain nameless out of courtesy for the OpenSearch community. This is not OpenSearch, but we have done this case study. We ingest a bunch of vectors into the database. We're sequentially, right? We're doing this in 2 different steps. Ingest a bunch of vectors and then measure the amount of time. We start the timer and we say, okay, now start indexing. We notice here, the gray here is that time that it takes to ingest the vectors, to get them into the vector database, right? This is not really including the GPU today. So we notice that it takes about the same amount of time. This is all disk and network I/O, right? Not the bottleneck on the CPU, right? It's clear that the indexing was the bottleneck on the CPU, but on the GPU, we notice it becomes the primary bottleneck. So we could keep shrinking the green there down to almost nothing, and we're still going to have an issue with the gray, right? Diminishing returns. And we're continuing to work on this, but being able to see still almost 7x speed up end to end with that, 21x speed up for just the index build, and then being able to reduce the cost if I can repurpose that GPU by 12.5x isn't bad for an initial case study. If I scale up even further and I start getting into the terabyte range, I take a terabyte of raw text, I get 2.5 terabytes of embeddings. It's going to take about 11.5 hours. This is both on the CPU and GPU to ingest that into the database, but then I can use 8 GPUs to crunch through this indexing in 56 minutes. And we've done some different weak scaling benchmarks, found it's a fairly linear speed up. If I add more GPUs, add more CPUs to be able to crunch through these numbers, then my multiplier of benefit is that much, right? We calculated that it would take 6.22 days to do this on the CPU, right? So you're talking about weeks down to minutes. Now, stepping back, we often have folks coming to us saying, hey, I measured the build time for this for HNSW on the CPU, and it took 5 seconds, and then I measured the build time on the GPU, and it took 30 seconds. And that's all they tell us, right? And the reality is these machine learning models, you have to realize these machine learning models, the vector search algorithms, they're different than traditional database indexes, right? You can pretty much guarantee a traditional database index, right, B star tree, whatever, it's going to give you a result. It's not going to be a garbage result if you don't tune it. If you don't tune a vector search algorithm, you could very well get garbage results, right? They have parameters that you set to be able to trade off, your quality, your search speed, and if you don't tune them, they're not going to generalize to every data set, right? So the next thing I would ask them is, well, what recall level do they actually hit? And they'd say, okay, well, the GPU version hit, 99% recall. The HNSW hit 80% recall. Okay, well, That's great, and that kind of explains what happened, but it's still not the whole story, because it's not good enough to just say that you hit that quality, right? Because those parameters, when we're trying to compare these algorithms side by side, you still have to be able to guarantee that we're at the optimum for both, that we're giving both a fair chance. And I'm not saying this because necessarily that we care about trying to give this GPU a better chance, right? We want to be transparent, we want to be honest, we want to know where we have weak points. We do this by creating these Pareto curves, and we create those by taking all of the different parameters that are possible for each algorithm, and we literally run all of them. And then we take the optimum from both, this trade-off between the search latency and the quality. So we make sure that these curves allow us to say, okay, at 90% recall, what does this curve look like? Where is it? What throughput are we getting? It essentially allows us to compare them side by side more fairly. So we'll take recall windows, usually everything 80% and above, we break them down, 80 to 90%, 90 to 95%, greater than 99%. But instead of just taking the lowest build time, right, which is, these curves are going to err, the lowest build time is probably going to be the one that has the worst search latency. So instead we just average, right, because we're looking for a summary here. This isn't something you would do in production, right? In production, you're going to use some different machine learning techniques like hyperparameter optimization to kind of learn the space without having to build 1,000 different indexes to do so. But this does allow us to compare these algorithms fairly side by side. So I think it's important to point that out. You're going to see these charts all over the slides. You've kind of seen them already from the beginning. So phase. Phase is wonderful. We used phase at the very beginning of some of our initial machine learning libraries for data mining. Phase is a really popular library out of Meta's FAIR research organization. They've pioneered vector search. They pioneered vector search on the GPU. This is where I want to give credit to them. They've also pioneered the interoperability between CPU and GPU. So this isn't something we came up with at NVIDIA. We've been using phase for a long time. We have a wonderful relationship with Meta. We entered a contest back in 2021. We ended up taking first place from the contest. It was using a phase algorithm as a baseline, trying to show billion scale. Long story short, we went to them and said, hey, we could just give you guys the implementations of our algorithms, but you know what, instead, why don't we create a library? We will maintain the library. We'll make sure it's always kept up to date as new architectures, new CUDA versions, new instructions are released, right? And that now has become the cuVS backend for phase. So this was kind of step one to being able to enable the OpenSearch integration. You'll see here the Pareto curve. I'm converting CAGRA graph to HNSW here. The build times are a lot faster. And then this Pareto curve, the fact that these overlap pretty much shows you that you're not losing any quality by doing this. Same here. You see the gap increase as we start to increase the number of dimensions, right? We go from 8.2x to 15.5x. And so now we have a vector search on the GPU in cuVS. We have interoperability with phase. We can build on the GPU. We can deploy it to CPU for search. You could even go the opposite way if you really wanted. Now we need to get it inside of a vector database. And so this is when we approached AWS OpenSearch team. We've been working with Vamshi, Navneet, Dylan Tong, the product manager over there. They've been wonderful. So we've been working together for about a year and a half now. This required some innovation on the OpenSearch side, and I'm not going to go into this too extensively because there are two talks today that I would like you to see. At 10:20, Vamshi is going to talk about trillion-scale vector search, which also covers some of the GPU acceleration, and Navneet's going to be talking at 11. So Vamshi is going to be in the Regency Ballroom here. Navneet's going to be in the Crystal Ballroom talking about the architectural changes. Just to summarize, these architectural changes included pulling out the build into a separate process, into a separate service, right? So that we could spin that service up, we can scale it out as needed. You could even build, if you wanted to, a serverless infrastructure from that. There's a wonderful blog that was published about this. I encourage you to go see that blog. Initial results look great, right? As you'd expect, the index build times are great. You can really lower the cost as well by being able to use this approach effectively. But we still have that issue with disk and network, right? That's the problem that we're solving now. So kind of looking into the future and looking into the next steps, right? The disk and network are a problem. So we have a new technology at NVIDIA called S3 over RDMA. That is, if I have an RDMA-enabled NIC, right, I have any other type of device inside my box, inside my instance that is RDMA capable, this doesn't imply GPU on either side, right? This is the CPU path, right? Being able to do this disk I/O. I can utilize that S3 to get that RDMA through the S3 protocol to get an additional 2 to 3x speed up. You can see over here, I brought a 5x speed up, now end to end, to an 8x speed up. So that's great, right? If we look at PCI Express, we also kind of see this exponential here, right? In the bandwidth capabilities, that MIOps there is millions of IOPS per second. Millions of IOPS per second. And we're not just talking about millions of IOPS per second. We're talking about hundreds of millions of IOPS per second. This hardware is a lot more capable than what we're doing with it. But this capability requires good software to take advantage of it. And so we call this effort Storage Next. At NVIDIA, we're always looking forward, right? And we always call it, okay, what is the technology next, right? And this is Storage Next now. Storage is a big deal. And so we're not just thinking about accelerating compute-intensive tasks anymore. We're talking about now accelerating data-intensive tasks, right? So this brings a whole big future, right, in the capabilities that we can provide. You know, every 3 years, around every 3 years, we have a new PCI generation. You know, we go from 50 to 100, we double it again. IOPS is usually more important when we're talking about random access. So for instance, I want to be able to put a graph on the disk, right? I want to oversubscribe my RAM with a graph, like a CAGRA graph or an HNSW graph, right? And in order to take advantage of 100 million IOPS or 200 million IOPS, I need to be able to schedule that many I/O operations at once, right? A CPU is not typically going to be able to do that with limited parallelism. Even with a couple hundred cores, I'm not really going to be able to take advantage of that. But if I have a GPU and I'm able to now have thousands of threads or hundreds of thousands of threads in the GPU, oversubscribe, right, and be able to make use of all of those IOPS, now I can actually saturate the bandwidth with random access. So this is the kind of stuff that we're working on now, right? So it kind of changes the picture a little bit. You're no longer concerned with trying to turn all of your I/O into sequential I/O just to make it efficient. It is true that now I can start thinking about random I/O in that way, which is for graphs, right? Traversing a graph is fine-grained random I/O, right? You don't know where you're going to be in that graph and where you're going to traverse. You put all these bits on disk, and it's all random access. And so it's not a surprise that we're seeing disk-based indexing picking up popularity, right? Because disks just make sense, right? Why would I continue scaling out nodes, paying for new hardware, when I could just make use of the disk? It's cheaper to put a disk in a system than it is to buy more RAM, right, in general. So it's not surprising. We've been working with a storage company called Kyoxia. They make the disks for a lot of our DGX machines. They're out of Japan. They have created a new library called Isaac, which initially was a simple improvement over disk ANN, right? They took the compressed vectors from disk ANN, they put them on disk. They came to us and said, hey, we put the compressed vectors on disk, so now they don't have to be in memory. The latency is twice as slow. What do you guys think? And I said, well, wait a minute. Why do you guys have a new library to do that? That doesn't make sense. Contribute that to disk ANN. So fast forward 8 months, right, and they come back to us. They've done all this amazing stuff to enable storage next, right? They've got all these new features, all these new capabilities. I see this as part of the future. They're starting to integrate Isaac into different vector databases. I'd love to eventually see it inside of OpenSearch as well. Imagine building these indexes on the GPU, then being able to use Isaac on the CPU, but then also having storage next involved. We have another technology called SCADA. And SCADA is kind of the vehicle that allows this storage next to be possible, right? Imagine now being able to completely remove the CPU from the I/O mix, like completely, and having each GPU thread now having its own independent access to the disk, right? This is kind of where we're headed. So I know I'm a little bit over time. Thank everybody for bearing with me here. Just to summarize, we've got cuVS, which is a library for vector search on the GPU. We've got Phase, which integrates cuVS, makes a great vehicle for being able to do interop between CPU and GPU. And when Phase has been integrated into OpenSearch, well, Phase is integrated into OpenSearch, it makes a super powerful story. OpenSearch has enabled the offload of the index builds, which also allows scale, which allows serverless technology. So thank you, everybody, for listening to this talk. Grab my tea.
Awesome. Thank you so much, Corey, for taking us through a deep dive in NVIDIA's work. I'm really excited to see the vision of the future come to life. Let's give Corey another round of applause for joining us here today. So, as technology leaders learn about OpenSearch's performance and capabilities, they often think about, like, how can I use OpenSearch at my company? And more companies are migrating to OpenSearch. And so I'm really excited to have with us today Hariharan Gandhi from SAP to talk about, he's the tech lead for SAP's cloud logging service, and he's going to walk us through their journey.
Hello, and good morning, everyone. I'm super excited to join you all here. It's also really inspiring to see a lot of passionate people gather around OpenSearch here. Last year, around May, I had the pleasure to join and speak at OpenSearch conference in Berlin. And here we are today in North America. Just in this short time, the OpenSearch project, the community and ecosystem has grown tremendously, making significant progress. Over the next few minutes, I would like to explain and share with you SAP's journey with OpenSearch or towards OpenSearch, and how OpenSearch has become a foundation enabling observability for SAP's business technology platform. My name is Hariharan Gandhi, and I'm a tech lead at SAP Germany, focusing on SAP Cloud Logging Service. I'm a distributed software engineer, focusing most of my professional experience on building observability service and hosting them. Before we start with the journey, I want to explain the environment that we operate in. It's the SAP Business Technology Platform, or in short, BTP. BTP is SAP's platform as a service offering that offers a comprehensive set of runtimes, services, and tools. It's SAP's innovation platform that helps thousands of customers worldwide to build, extend, and integrate intelligent business applications. If you take a look at the foundation of BTP, BTP offers multiple runtimes, such as Cloud Foundry, Kima, the ones that you see in the bottom left. It is on top of these runtimes that both SAP business service teams and customers build their workloads. I'll talk about the open source aspect of these runtimes later on the slide. Given the sheer scale and variety of services within SAP BTP, observability becomes really essential to ensure the reliability and performance of the workload that runs on top of them. This is where SAP BTP observability comes into play, the area where my team belongs to. And we offer SAP Cloud Logging as a hosted observability service to cater to the needs of observability on BTP platform. To fully harness the diverse and powerful suite of runtime services and tools, it is essential that we adapt a unifying standard. So rightfully so, we see increasing adoption of OpenTelemetry within our platform. This is very crucial because OpenTelemetry allows us to seamlessly correlate and unify data across our landscapes. OpenSearch, with its observability capabilities and also support for OpenTelemetry, sounds like a perfect fit to power our SAP Cloud Logging service. Among the impressive list of capabilities that OpenSearch offers, powerful search, machine learning, AI, security capabilities, our main focus is observability. OpenSearch plays a central role in enabling observability for BTP. Our DevOps start using Cloud Logging Service right from the development phase, use our 4 golden signals to monitor their application in production and detect performance degradation, and also use the advanced capabilities to perform troubleshooting and root cause analysis once the incident has occurred. We fully leverage the capabilities of OpenSearch, log monitoring, performance monitoring, service topology, visualizations, alerting, and all observability capabilities. I want to highlight the particular capability of OpenTelemetry support. This is particularly valuable as it allows us to standardize how the data is collected and easily correlate logs, metrics, and traces for efficient troubleshooting and root cause analysis. This allows us to slowly move away from proprietary protocols specific to certain runtimes and use a single standard way of collecting and visualizing observability data. We were one of the early adopters of the OpenTelemetry support, and the OpenSearch data prepper and OpenSearch visualization for OpenTelemetry makes the life of this OpenTelemetry adoption easier. With OpenSearch powering our SAP Cloud Logging service, it offers a comprehensive observability solution based on logs, metrics, and traces for the developers and operators hosting their workloads on BTP. After 2 years of testing internally and seeing immense growth and adoption, we made the service public by end of 2023. One of the key highlights of SAP Cloud Logging service is its ability to cater to non-observability users. So I'm a business, I want to build a business application on top of BTP. I don't want to care about hosting observability service, managing them, and even know how to build a dashboard and things like this. So it is to this non-observability use case that SAP Cloud Logging service caters to. So when a developer builds his application on one of the runtimes that BTP offers, within the runtime, he can also choose to provision SAP Cloud Logging. And the SAP Cloud Logging service takes care of smooth integration with the source from the particular runtime, understand the protocol of the runtime, and enable ingestion from there. On the other end, it offers out-of-the-box dashboards like 4 golden signals, service quality dashboard, and so on, that the developers don't have to spend time to understand the different formats, protocols, parsing, and building visualizations. So it's available for them right out of the box and gets them started right away. On the other end of the spectrum, we also have power users. They are proficient with OpenSearch than we are, and they want to use the rich capabilities of OpenSearch all by themselves. Thanks to OpenSearch's advanced capabilities, we can also offer them directly to cater to the needs of such power users as well. Okay, now that we know about the service and the environment that we operate in, let's start about the journey. The journey with OpenSearch did not start overnight. It was driven by clear needs. The need for a hosted observability service. Excuse me for a minute. The need for a hosted observability service for the platform to enable insights for the users building services and application. And it also wanted to be an open solution that could be easily extended and comes with a reliable open source characteristic. We also wanted to focus on the enterprise quality of this open source software. It needed to be compliant, it needed to have a set of configurations that makes it compliant with different environments, a proper authentication and authorization, and so on. And last but not least, it has to come with a strong and trusted community and a clear roadmap for future innovations. So these qualities shaped the decisions that we took down the road. About 10 years ago, a decade ago, we started our journey by using open source version of Elasticsearch as the engine to power our BTP logging service. It was quite a fit at that time for the use case that we had. We wanted to offer a logging service for just one of the runtimes that BTP offered. It was a read-only mode service, so you can only view visualizations that we offered. It was a good fit at the time. To talk about the open source characteristics of this one, while the underlying Lucene was truly open source, the Elasticsearch open source was predominantly steered by one particular vendor. We had fewer community interactions, and for SAP this meant limited involvement and obviously the risk of license. The open source version also lacked some of the basic capabilities of observability, like for example, authentication and authorization, alerting capabilities, and so on. There was also a parallel commercial version with such advanced capabilities available in Elasticsearch. This restricted our ability to innovate and fully involve in the open source space. Evolution from this stage could be categorized into 3 phases. And the first phase to overcome these limitations, we started building our own custom enhancements, like, for example, alerting module or security module. Since we were focusing on just one of the runtimes, we built our own security plugin. Our module, I have to say, it's not a plugin, and made it open source. It was based on OAuth, and so on, and it worked quite well. But the maintenance of this custom implementation turned out to be painful, because for every version update, we have to ensure the compatibility of this custom enhancement. And the security module in particular was really crucial because there is no margin for error, like with alerting or something else. So this greatly limited what we exposed as capabilities to our customers, even the free open source capabilities. It was at this time we were also rethinking to rebuild our observability stack. So we wanted to build it in a massive scale using Kubernetes. We also wanted to support more runtimes, or we wanted to be agnostic to any runtime that BTP offers and so on. And when we were thinking about this replatforming, we were looking for alternatives. And it was at this time AWS made OpenDistro for Elasticsearch open source. We're really thankful for this contribution. And we started evaluating OpenDistro for Elasticsearch in our beta versions. And this was going on. Shortly following this, there was this disruptive change in license and the shift towards non-open source license made it not usable for SAP. Like for many of you, it was a disruptive change and turning point for SAP. Closely following that, there was the open source fork of open source Elasticsearch. Amazon took the lead here and initiated the project. We are really thankful for the initiative and the investment that they did here. We were immediately drawn towards this project for quite some reasons. Right from day one, it was positioned as a community-first project. We were initially involved and invited for certain events, decisions, and so on, which we felt is really open. And I still remember the days when they were also collecting feedback on the logo designs. I think it still happened on the OpenDistro forums. So it looked very open to us. And there was also, from early on, a strict focus on quality. As an enterprise company, it was a good sign for us. Over time, there was an impressive set of innovations presented in the public roadmap. For SAP, this openness is what we were looking for. So we started our assessments to adapt OpenSearch. So we had two sets of clusters that needed to be migrated to OpenSearch. The ones that ran 7.x version of Elasticsearch open source, and the ones that were running OpenDistro for Elasticsearch. Thanks to impressive set of documentation, it was a smooth transition to OpenSearch 1.x. After our initial assessment, we initiated the migration project for our SAP Cloud Logging Service beta version, and it had at that time around 10,000 OpenSearch instances. And we quickly started seeing the benefits. We could get rid of the custom implementation that we had. We already did so when we used OpenDistro. And our involvement in this community also started growing slowly. We started contributing and involving in topics like OpenTelemetry, Data Prepper, and participating in events. We also saw ever increasing value for the rich, not just for SAP, but also for the users and stakeholders of SAP about this open source community. I want to jump ahead in the timeline to talk about today. So today, we run around 11,000 OpenSearch clusters on Kubernetes. To keep them up and running and to manage them, we use Kubernetes operators. We saw a significant improvement need in our Kubernetes operators to upgrade such massive scale of clusters. So we wanted to take a pause before upgrading to OpenSearch 2.x and invest heavily so that with the goal of making our operators update our clusters in a ZDM mode in a way that it could throttle the update and so on. And I'm happy to say that we have achieved this improvement in our with our Kubernetes operators, and today SAP Cloud Logging Service can upgrade to OpenSearch 2.x already. And this has already prepared us for easier migration to 3.x, and we are looking forward for that. I have a talk tomorrow about explaining the setup that we have here. I could have stopped the presentation with the last slide, but the commitment of the OpenSearch project team towards open governance took it to the next step when they established the OpenSearch Foundation under Linux Foundation. The picture that you see here is from the Open Source Summit in Vienna, and the speaker is Gabriela Colombo. And this slide highlights two key aspects that were really important for us. A level playing field for all the participants, like SAP participating in this community, and keeping open source open all the time. So these two key characteristics amplified the trust we have, and not just us, but also for the community. It amplified the trust on this OpenSearch project. We truly believe that open source communities allow co-shaping innovations and driving innovations together and with great quality. We also saw this perspective change within SAP and also the stakeholders of SAP. So right from day one, SAP jumped in and became a premium member of this foundation. And we also started taking up active roles in the foundation. We have Verena Lomac, the head of SAP BTP Technical Services, representing us in the governing board. And we have Carsten Schnitter from SAP Cloud Logging Service Architect, representing us in the technical steering committee. It has been 1 year since they took up the role, and the experience so far has been phenomenal. Being collaborative and constructive planning, working together as a team. And this committee involves people from different organizations across the globe, but they still act as one big team. So kudos to the members of the foundation to bring this spirit. This involvement means that SAP both benefits from and contributes to the community and takes care in the long-term sustainability of the project. We want to co-innovate and co-drive innovations with all participating organizations. You saw from Carl's slide the impressive list of organizations from across the globe contributing to OpenSearch. It is also our goal to engage with other communities, learning from each other and also sharing our experiences. These are all corporate motivations, but I also want to highlight the personal motivation, the change in the mindset of individual contributors, for example, from within my team, once OpenSearch became a foundation. It motivated individual contributors to contribute to a software that's part of a prestigious foundation. So this is a clear shift and inspiring for individual contributors. Talking about contributions, I want to highlight three main areas where we are currently engaging. One is the enterprise readiness. We wanted to support with the FIPS compliance for OpenSearch Core. This would make the open source software suitable for environments that have strict regulations and even strict regulations. In the observability area, the main focus for us is supporting OpenTelemetry, events in the data prepper. We also contributed to index alias rollover in OpenTelemetry signals, and also looking forward to contributing the HTTP support. We run one of the largest deployments of OpenSearch on Kubernetes, and we learn a lot by doing so. So we also think it's really valuable to give this feedback that we learn from these, we learn from running such large-scale clusters and give the feedback. And hot off the press, the establishment of technical advisory group, OpenSearch Observability. This TAG is focused on providing strategy and guidance for observability around OpenSearch ecosystem. So we also join and contribute there with our own Carsten Schnitter and Jürgen Walter. Coming back to this illustration that I had before, on the bottom right you see the runtimes, Cloud Foundry and Kima. Both of these are open source runtimes and pioneered by SAP predominantly. schema, in particular, is a Kubernetes-based runtime, and it is powered by Gartner. Gartner, again, is SAP's open source Kubernetes as a service offering, and it's also governed by NeoNephos Foundation under Linux Foundation Europe. So it is the Gartner that enables us to maintain a fleet of Kubernetes services, or Kubernetes clusters. Our cloud logging service also deploys on more than 50 different Kubernetes clusters, and it is made possible only with this open source Gartner. On to the left, you see OpenTelemetry. I had already highlighted the benefits of OpenTelemetry and the slow adoption of OpenTelemetry into our runtimes. This also helps standardize the way how we produce and consume data. With OpenSearch bringing all of these together, supporting traditional runtime observability needs and also emerging OpenTelemetry standards, OpenSearch tries to bring them all together. Our aim is also to combine to not just innovate in one open source community, but also innovate across all these open source community so that the value multiplies and gives higher impact. So it has been a 10-year-long journey from our days of using Elasticsearch 1.x to current OpenSearch 2.x. I have to say SAP is really grateful for all the teams that contributed to this journey, and also to the community for being so vibrant. We are also very proud to be an active member of this community. And I'm looking forward for the next 10 years of innovation in this space here. Thank you so much. And thank you.
Awesome. Thank you, Hari. It's truly impressive scale, and thank you for sharing that with us. I personally got a nice little pang of nostalgia with the Open Distro shout out, so appreciated that. We're truly fortunate to have such innovative users setting the bar so high for OpenSearch and for observability applications. So, it's people like Corey and Hari and all the others contributing to OpenSearch in a variety of ways that propel this project forward. And as the community grows, the innovation curve continues to accelerate. But here are some numbers that will spotlight the community growth. But I'd like to take a second just to talk about this event here, OpenSearchCon. We first started OpenSearchCon in September of 2022 as a single room, one-day event in Seattle. And I'm really happy to see how it's blossomed. This year we did OpenSearchCons in India, Europe, North America, Korea, and Japan. And I'm excited to announce that next year we're taking OpenSearch somewhere new. So I'm happy to announce, we'll be hosting OpenSearchCon in Shanghai, March 17th and 18th. So please be on the lookout for that. There's been a lot of interest in doing an event in mainland China. And we'll be calling for papers here in a few weeks in Q4, so be on the lookout, and hope to see some of you there. I'm also honored to say that OpenSearch has a lot of fans. And these are folks that are eager to talk about OpenSearch and go out into the community, and many of you are here presenting about OpenSearch, would quantify yourself that way. And so as the OpenSearch Software Foundation figured, we ought to foster a program that recognizes and enables our most prominent advocates. So with that, I'm excited to announce that today we're launching the OpenSearch Ambassador Program. It's my pleasure to officially welcome the first 11 ambassadors to the program, 6 of which who are here and are going to be able to join us at the conference. So please let me welcome them to the stage. So I'd like to welcome Cassian, Nate, Amanda, Eric, Itamar, and Chris. Your first 6 of 11. There you go. Awesome. Thank you, guys. This program is all about recognizing and supporting passionate folks who go above and beyond to help the OpenSearch community grow, and to bring trusted voices to OpenSearch to the spaces where people are, be it meetups, online spaces, or beyond. We want to empower those leaders to keep doing what they do best, which is teaching, creating, and connecting. So our goal is to build a global crew of contributors, developers, advocates who are willing to amplify the community's voice, promote open source collaboration, and spark innovation. And this is just the beginning. If you'd like to learn more about the program, or if you're interested in becoming an ambassador, the QR code will take you to more information about it. So special thanks to our ambassadors, and I hope you'll look out for these folks throughout the conference and get a chance to talk to them and learn more about them. So there's one last thing before we wrap up, and one more person I'd like to bring out on stage. So I've talked a lot about the excitement in the community as around OpenSearch, as more and more organizations and people are getting involved. And from the OpenSearch Software Foundation, this is a great problem. It's now, how do we continue to scale? How do we maximize all of this momentum, all of this energy? And that's why it's great news to announce that we have hired our first executive director for the OpenSearch Software Foundation. And I'm delighted to welcome to the stage Bianca Lewis. To the foundation with an exceptional record of accomplishment as a business and community leader across open source and commercial. She included leadership roles at Logs.io and Opser, who are both members of this community. And I could not be more excited to have her take the reins. So,
thank you so much, Carl, and thank you for the warm welcome from all of you. You know, this is my first week in the foundation, so I'm going to keep my remarks super brief. I've had the privilege of being a member of the OpenSearch community for many years, as Carl has mentioned, and that's given me a front seat into watching the growth of our project. And especially since like the past year, since OpenSearch has joined the Linux Foundation, it's been quite remarkable. We've seen already today that we are on the wave of great innovation. This innovation is powered by you. Okay, you sitting in the room today, as well as people like you all over the globe, all over the world. So I could not be more excited, humble, and proud to lead the OpenSearch Software Foundation to build a future of OpenSearch together with all of you into something that we're all super, super proud of. So I am going to enjoy connecting with you all at the conference, as well as well beyond. So thank you, everybody, and thank you, Carl.
You're welcome. So thank you, Bianca, and thanks to all of you joining us here for the keynote, and let's make this a conference to remember. Thank you, guys.